In this activity, you're going to use gain and phase margins to talk about tuning a proportional controller for this unit feedback system with this system transfer function to achieve certain phase margin. And so what I'd like you to be able to do is be able to connect both the mathematical approach with our graphical approaches using the Bode plots directly. And so typically we won't do much of this analytically, but it's worth doing this once to see how this all connects together. And then I'd like you to observe this on the Bode plot actually using MATLAB. So the question is that if we're just going to choose K to be 10, I want you to go ahead and quantify what the phase margin is. So visually, that's rather simple. That's applying what we did before to look at the phase margin on the Bode plot. So that's what you're going to do second. What you're going to do first is to look at g of I omega, k g of I omega, and figure out both the magnitude and phase of this quantity. And when k is equal to 10, plug that in and figure out what the phase margin is kind of from this kind of mathematical approach. And so what I'd recommend doing is don't plug in values. You can go ahead and plug in what g of I omega is, but keep k separate and don't plug in 10 until you get the final solution at the end, and then plug in k is equal to 10. Because in the second part of this, what we're going to do is we're going to retune the gains. We're going to pick a different value. Instead of k is equal to 10, it'll be k is equal to something else, and we'd like to compute it so that the phase margin is 30 degrees. And so again, we'll do this analytically, and then you can also do this on the Bode plot. So go ahead and give that a try, and I'll show you my approach. Okay, so from an analytic point of view, if we want to compute the phase margin from a given gain, then what we're going to do is we're going to evaluate k times g at I omega. So that means that we're going to go ahead and plug in I omega into here. So this will be 1 over I omega multiplied by I omega plus 1. All right, and so we've done this enough times. I'm going to skip the steps where I essentially go from this into this format. So that's a useful activity if you think that you're not comfortable with doing that. But this is where you'd start, and this is where you'd finish evaluating k times g of I omega. So that what I've done here is I've broken this into a real part and the imaginary part. And so the magnitude is the real part squared plus the imaginary part squared, square rooted, and that gives me this gain. And then the phase is given by the essentially the imaginary part over the real part and take the inverse tangent. But to get the correct angle, we use this in atan2, which takes in two arguments, essentially the imaginary part and the real part. And instead of dividing them, we give them separately. But if we do have common factors like this k over omega squared plus 1, then we go ahead and cancel those out. And so then that leaves us with just minus 1 over omega. So that's this part. And then we just get a minus 1 that's left in the real part. And again, we can cancel out common positive factors, but these angles and the signs are important because what you're doing here is you're figuring out that when both of them are negative, you're going to end up in this third quadrant. And so that helps you figure out the angle. Okay, so these are expressions for magnitude and phase. So now what we're going to do is just evaluate. So when k is equal to 10, then we can go ahead and plug that in. We can go a little bit further with our math, though, is that we can figure out the phase margin. The phase margin is specifically where the value of omega, where the gain is equal to 1. So what we can do is we can set that gain as equal equal to 1 and solve for the value of omega that satisfies that. So in this case, we know what k is. Let's keep that not plugged in right now, just so that we can kind of keep it clear where the gain affects everything. So we're looking for the value of omega that makes the magnitude 1. So by rearranging this expression, we can get ourselves down to this expression, which says that I can go ahead and plug in my gain k, and that will give me the value of omega where I should measure my phase margin. And so then what I'm going to do is I'm just going to simply plug in the phase margin is going to be the phase at that value. So I'm going to plug this omega star in here. That's going to give me my phase. And then I'm going to see how far it is away from the minus 180 line. And that's going to give me my phase margin. So that's how we do this analytically. On the next slide, I'll show you the numeric values and how we get it from the Bode plot. If we wanted to use these expressions, though, to retune the gain, so now we're going to say what is k, and we want to guarantee a phase margin of 30 degrees, then what we'd do is we'd go up and we'd say, okay, we want this phase value to give us a phase margin of 30. So in that case, that means that the phase margin is 30, and so this quantity here would be minus 150. So we'd be trying to achieve a phase at minus 150 here. And so then we'd try to figure out, okay, since the phase is not changing as the gain is changing, we can go ahead and compute omega directly from that phase. So we say, we can say that 150 is our phase that we want is equal to a tan 2 of minus 1 over omega, comma minus 1, and we rearrange that to get that omega star, so this is going to be the omega star, in this case, is equal to the tangent of 150, 1 over that tangent of 150. And so that's where this comes from. And then we can rearrange this expression that we had for the magnitude in order to figure out what value of k we need to choose in order to make sure that at this frequency value, this omega star, this magnitude is 1. So we satisfy that marginal stability criteria. So now we know omega, and so we're just going to plug that in and figure out what k is. So when we do this visually, the way that we do this is we're going to just go ahead and plot the Bode plots when k is equal to 10. And so that means that we would call Bode of 10 times g, where g is this transfer function. And so we're calling that in MATLAB. And so it's important to keep this 10 in here because that's going to shift the magnitude plot up and down. And so what we observe is we get the blue curve in the magnitude, and then again the Bode plots are the phase of the Bode plots is the same in both cases that we're going to look at. So this is the phase down here, and so what we observe is this is minus 180, and so the phase is actually always above minus 180. Now it looks very close, like it's getting closer and closer, but it's important to realize that this is an asymptotic approach to minus 180. You can go back and look at how we wrote down the expressions for that Bode phase for different parameters, and you'll see that these are asymptotic limits. So this is actually, it gets closer and closer to minus 180, but it never actually crosses. And so this is an example of a system that is stable, that is closed loop stable for all values of k. So that means that it's always stable, but that still means that we can evaluate the phase margin. And so what we're going to do is we're going to take a look at for when k is equal to 10, we try to find a point where the magnitude is 1. So the magnitude here in dBs, so it's very close to 1. So the magnitude is very close to 1 because this is very close to 0 dB. So this is supposed to be as close as you can get to 0 dB. And that happens at about omega is equal to 3.08. And so that's this value right here. So that's where the blue line is crossing the 0 dB line. And now we trace that down here and try to figure out what that phase value is. So we try to figure out the phase value at 3.08. at that frequency. And again, this is the same as k is equal to 10 because the phase doesn't change. So at that frequency, the phase is minus 162, which means that the distance between minus 180 and minus 162 is 18 degrees. And so the phase margin at k is equal to 10 is 18 degrees. So that's smaller than what we want. And so when we retune, we'd like to pick a gain that achieves a phase margin of 30 degrees. And so what we do is we can find, again, this value of the phase that we want. So that phase of minus 150 is going to give us our phase margin. That's going to be our phase margin that's equal to 30 degrees. And so that happens right here where the frequency is 1.73. And so what we're going to do is we're going to come back up here to our existing line at k is equal to 10 right here, and that's at frequency 1.73. And so if we were to evaluate that point on the blue curve, that would tell us the magnitude at that point, and it would also tell us how much we'd need to reduce the magnitude in order to make that equal to 0. Because remember, multiplying by a smaller number is going to reduce, smaller k value is going to reduce and shift this Bode plot down. So you can either do that through experimentation, or you can figure out what that gain value is here and how much you need to reduce the gain k in order to get you down to a point where the magnitude is 1 or very close to 0 dB at this frequency here, because that's the frequency that's going to guarantee us 30 degrees phase margin. And in this case, again, you can either do that analytically, like what we showed on the previous slide. You can find this gain on the blue curve and figure out how much you have to reduce it, or you can do some trial and error, and we're going to eventually see some tools where you can easily slide this around. Shows us that a gain of 3.47 is what achieves the magnitude curve crossing the 0 dB line at the frequency of 1.73, which is the same point that gives us phase margin of 30. And in this case, there's only one point that will give us phase margin of 30. We will see some examples where it's possible to get multiple places where you could shift the curve in order to get 30 degrees or any other phase margin.